Okay, hello everyone. Thanks for coming. I'm Ziwei Wang from Nanyang Technological University, and my research focuses on embodied AI and robotics. Today, I'm very glad to introduce one of important topic in embodied AI, which is embodied visual perception in unknown environment. So as we know, robots have been applied in many applications, such as home services, manufacturing, and warehouse logistics, with very high generalization ability. So for the home services, we can imagine that we have a home assistant in our home. We can ask a robot to do a lot of household tasks like cooking an omelet, tidying the bedroom, and cleaning the bathroom. And for manufacturing, we can do a pick and place and assembly. And for warehouse logistics, we can use a robot to reduce the accident rate and increase the throughput. So we mainly focus on household tasks because household tasks, I think, has the largest customers, and which is also a challenging topic because in our indoor scenarios, the scenes are always very cluttered and complex. So this task can be defined like this. Given a human instruction, for example, please serve my guest with a hot tea. So the robot should physically complete the actions in this household scenarios. So the pipeline, this task can contain 3 stages. The first one is to parse the human instructions. For example, what are the stepwise actions for the robot to serve the guest with a hot tea? For example, step 1, going to the kitchen, and step 2 and step 3. So after that, we have the stepwise plans. And in the stepwise plan, we actually have the target object. For example, in the step 2, the target object will be the kettle. So we need the agent to find the target object like the kettle in a large house level scenes. This is actually very challenging because the house is usually very large and the object is very small. And finally, after we find the target object, for example, if we find the kettle, we needed to do the actual physical manipulation in the real world to generate some manipulation policies, including the waypoint, including the pose and the locations of the grippers. So actually, this is a complex system, and we only focus on the perception part, which is the finding the target object in a large scene. So you may say this actually can be done by a high-level planner and a low-level controller. For example, we can use LLM or other planners to generate the stepwise plans for the human instruction. And based on the instruction, we can use current visual navigation algorithms to find the target object in a scene. But actually, this is not feasible in practical scenes. Let me show you an example. Because if we just use a planner, for example, if we use a GPT-4o as a planner, we ask the large language models to generate the plans to cook a lettuce for breakfast. So this is a common sense. We need to find a lettuce. We need to find a pen. But in many things, we do not have a pen. So if we just use the generated actions like move to the pen and ask the robot to find the pen, it will be failed. It will be stuck in finding a pen, and the whole task sequence will be failed. So you might ask, can we just build the scene map before the robot start to work? The scene map just records the locations, the object, the category for objects in different locations. This is actually often used in current navigation algorithms, but this is also infeasible because we have a lot of human activities in our household scenes. For example, when we are like using a laptop in a study, the mugs for water drinking, maybe put on the table or in a study. But if we are having dinner, the mugs may be put on the dining table. And this is the first one. It will change the locations of the objects. And the second one is that it will change the existence of the objects. For example, today, if we ask the robot, the agent to cook a breakfast for us, and for Monday, for example, we have potatoes, but we have consumed all the potatoes on Monday, and we buy some eggs for Tuesday. So if we use a pre-built scene map on Monday to generate the task plans on Tuesday, then it will fail because we don't have potatoes anymore. We just have eggs. So the last question is, can we just build the scene map, pre-build the scene map before every time before the robot start to work? This is actually not feasible because if we want to build a scene map, it will take a long time. For example, it will take like a half an hour to an hour to build a scene map for a house, over 100 square meters. So if every time, for example, we ask the robot to make an omelet, the robot need to spend like a half an hour to build the map and then do the omelet. So actually, we need an online scene map. So for the online scene map, which means that we can update the scene map, which is a visual representation of the scene at any time at each frame, because the data stream just arrives sequentially during the navigation or other embodied tasks. For example, in different time steps, we will collect the different RGBD images. And then we need to ensemble all the current RGBD images with a history RGBD images to form a memory like a scene map, and use this scene map to do a lot of downstream tasks in real time, such as from the low level semantic segmentation of detection to the high level navigation and manipulation. And the second thing is that we need to find the object, right? We need to find the object that is related to our task. But what is the object that is related to our task? For example, if we want to ask a robot to make a breakfast, we have a lot of food in our fridge or in a kitchen. So what is the target object? So our second solution is that we use multimodal large language models based on our online scene map to find the task-related object. That is different from the conventional object goal navigation, because conventional object goal navigation has a specific goal, but we are task guided. So for the first part, for the online scene map, actually, our idea is very intuitive. So in the online scenarios, we usually use RGBD string for the visual perception. And because we have a lot of very good 3D and 2D backbones, we can just design the plug and play module after the current backbones and enable them to do the task in online settings. So in a plug and play module, we have a memory that records the history information, and we have an adapter that adapts the information from the memory to current features for the boosting. And after that, we get the a semantic or instance segmentation or object detection result, and then we fuse the current result with a history result. So for the 3D part, I mean, for the point cloud part, actually, it's very intuitive. We just voxelize all the point cloud and then do a max pooling between current features and the memory features. And after that, we get our memory in the bottom line. And after we get the memory, we can query the memory with the current feature based on the neighborhood and enhance the feature. And after that, we transfer it back to the point cloud. And for the image part, we just do a shifting. And we shift in the current features to the memory and shift out the memory to the current features for the feature enhancement. And then for the 3D to 2D adapters, we just project the point cloud to the images and then crop the images to do the fusion between semantic information and geometric information. And this is our result. And you can see SV means we just directly use some SOTA 3D object detection or semantic instance segmentation algorithms. For each frame we collect during the whole sequence and concat the detection result or segmentation masks for each frame directly without any further operations. And you can see our method can improve the MAP by a large margin. And even our method is comparable with a reconstruction-based method. So, but we have two advantages. The first one, our time cost is much lower because reconstructing a scene may need like a half an hour or 20 minutes, but we can just do it online. And the second one is that we have a higher generalization ability for incomplete point cloud, because in the practical scenarios, we always can only collect the incomplete point cloud. So we need our model can work when we encounter some incomplete point cloud. And this is our visualization. So this is SV. This is the reconstruction-based method, and this is our method. And you might see, compared with SV, our predictions, like you can compare these two, our predictions are temporally aware, and we have less positives. That is because for the SV-based method, they just combine the different object detection results directly, but it is hard for us to distinguish whether the bounding box between the consecutive frames are the same instance. So they have a lot of false positives here. And compared with offline, as I just said, because our method is trained among, with a different completeness of the point cloud. So it has higher generalization ability to different scales of scenes, for completed scenes, for incomplete scenes, for partially completed scenes. Okay, this is a video demo for this one. So this is object detection. We have a human just hold real sense RGB cameras, and it can generate the bounding box, object detection bounding box in real time and at any frame. So we can actually choose the length of navigation based on a budget for data collection. And this is in instance segmentation. And you can see we can also generate the 3D masks in real time. Okay, after that, the next question would be, how can we find the task-specific, the task-related object, target object, based on our online feature map? So this is actually very important. Let me show you the example again. So if the robot is given the instruction, I need to drink water. So if you directly ask GPT-4, it will generate step 1, I need to find a bottle. So in this known region, if this region is unknown in realistic things. So, but unfortunately, in this scene, we do not have a bottle. Although bottle is a very common object to carry the water, right? So conventional method will do a replan. So it will try the glass again and then try different solutions. But actually, this is somehow like an enumeration of all possible objects that can accomplish these human instructions. And this is very time consuming. Let's imagine if we ask a robot to do make a breakfast. So we have a lot of food that we can choose for the task planning. And this cost a lot of time for the robot to do a different trials in a large scene to see whether we have an egg, whether we have an apple, whether we have a lettuce or something like that. So what we want to do is to ask the model to directly output what we need to have or what we need to find to complete the human instructions. So we use large language models, multimodal large language models. So compared with the ordinary large language models, we also have the human instructions, the done actions, and some state of the robot, for example, for the input. But besides, we also have the visual input here. The visual tokens are actually our the online scene map just built in the last work. We will generate something like a simple as plans to find open the box, and this is actually the reasoning result of the multimodal large language models. This is one that the LLM think we can find the object with the highest probability, and this is actually related to the task. And after that, we will use a low-level controller for navigation policy generation. And besides the language input, like the step planning generated by the high-level planner and the frontier descriptions. The frontier just means that we have a lot of frontiers between the known region and the unknown region. So the navigation controllers need to select one of them as the optimal navigation policies. So this is a coordinate of all frontiers. And also with our visual token, the online scene maps, we will generate which frontiers shall we select for further navigation. So in the above pipeline, the most important thing is that we need to build good online scene map. So this is actually a little bit different from the low-level tasks like 3D segmentation or object detection. We need to figure out the spatial correlation and the semantic correlation among different objects in the indoor scene environment. So actually, we need richer semantic information and of this scene. So we will update the scene map like this. So we will extract the visual features for each pixels in the RGBD images by a pre-trained models, like we use a concept fusion or something like that, and project the feature in the top-down view to build the scene map. And because different images collected during the whole sequence have different importance. For example, if we want to make a breakfast, the robot will navigate the house, right? But the visual features in the bedroom is not important if we just want to make a breakfast. But in the kitchen, it will be important. So we will calculate the importance of each image when we update the feature. So we will design 3 statements like this. The image contains one of the target object. This is actually the target object generated by the planner. And the second one is the image does not contain. And the third one, according to our empirical study, is very important to set this like a default one. So the image does not contains nothing, which means the robot just faces to the wall or faces to the ground. And if we do not have this, the performance will decrease by a large margin. So we will use the probability of normalize the probability of this statement as the importance weight and add the visual features of the current frame to the history feature maps using this importance weight. And we can show some visualizations here. And let's say we have a instruction, fetch an apple for breakfast. So our model, our planning, high-level planner can generate something like move to the fridge to find an apple. So obviously it'll find the correlation, semantic correlation between the apple and the fridge. And after that, it need to find a sink to wash the apple. Because in this scene, we do not have a sink in the kitchen. We just have a sink in the bathroom. So the low-level controller may explore the frontier between the bedroom and the bathroom instead of exploring the frontiers between the two bedrooms. So this is what the low-level controllers, navigation controllers, learn. And we also have a demo in the simulator. So this is the first view RGB images, and this is the third view images of the fetch robots in the simulator. And this is our CMap. But this is not actually the CMap, because for visualization, we just project the category of each location in the top-down CMap. In our realistic CMap, we have some implicit features. So you can see this is a trajectory of our robots in finding the object. So this is it needed to find the fridge. So to do a lot of errors and trials, and finally it will find. Let me speed up this one a little bit. Okay, here to find the tomato, and then the next one would be pick it up, and then clean, and after that, so it need to find a sink like the last examples to in the bathroom, and then to place and use a knife to slice a tomato. So you might see, although we have increased the efficiency of finding the target object, the efficiency is still low because we need to have a lot of errors and trials to see whether the fridge is in that place and the tomato is in the fridge. But you know, as our large language models has a lot of common sense here, and if we can build organize a structured representation of the whole scene, we may accelerate the process of the object search by navigation. So actually, this is always what the zero-shot object-go navigation does in a conventional methods. But in a conventional methods, they just figure out the co-occurrence correlation. For example, the TV is next to sofa, chair, and the table. And this is not enough for our navigation robot, because let me show you an example. If we just want to find a TV, of course, the target is given by our previous work. If we have a target like TV, find the TV. So we only know the TV is next to sofa. So the robot may navigate to the space behind the sofa to find the TV. Obviously, it fails. So our solution is to build a fine-grained, like a scene graph for this one. So we have a hierarchical scene graph in 3 hierarchical levels because we have a lot of objects in the house, right? We need a hierarchy to reduce the redundancy. And we have a room level, we have a group level, and we have a object level like this one. Okay, we have 2 main ideas. The first one is that we just build the scene map during the navigation process. And this is actually very intuitive. We can just use like a grounding sand or like something like this to figure out, for example, this is a potato, and this is a sink, this is a microwave, something like that, and build the scene map by some heuristics. And after that, we will prompt the large language models with our hierarchical scene graphs. And the large language models will generate the score for each frontier, and we will calculate which frontier has the highest score, and then we will navigate to that score as our navigation policy. Okay, this is our quantitative result. So you can see compared with zero-shot navigation method, we can increase the success rate by a large margin here. And our method is training free. So compared with the supervised method, we don't have any training cost. This is actually very important because currently many works just use large language models or multimodal LLMs. If we need to train the robot, we need to collect a lot of data, and we need a lot of computation resources here. And the second one is that we have better generalization ability, because in our household scenarios, generalization to novel objects, to finding novel objects is very important, because we always buy something from the supermarket, from the Amazon, something like that. So we need the robot to find the novel objects. So this is a visualization of our zero-shot goal navigation. So we have this is the occupancy map here, and we will build a hierarchical scene graph during the navigation process. So you can see after the bedroom node, this is a room level load. We have a bedroom furniture. This is a group node, and after that we have a chair and a bed during the whole navigation process. And use that we find the cabinet finally. Okay. So for the future directions, I think although currently we can find the task-related objects given the human instructions, but we still have two challenges. The first one is multitask, the general scene representation. Why we need this? Because in the embodied tasks, like the household scenarios, besides the navigation, besides object finding, we have a lot of other tasks. For example, we need to manipulate the fridge, right? But in our current work, we can just find the fridge. We cannot open the door of the fridge. And so we need a scene representation across different tasks. So one possible solution might be the multi-scale scene representation, because different tasks just focus on the different scales, different information in different scales. For example, if we want to do a navigation, we just need to know the object categories. What is that? What is this in this location? But if we want to do a manipulation, we actually need to know the fine-grained geometry of this target object. If we want to open the door, actually we need to know the geometry of the handle of the door, so we can operate the handle to open the door. And the second one is that we need to combine our online scene representation with foundation models, because we have a lot of visual foundation models like Dino, like a SAM. If we can use them, we can increase the generalization ability to some novel objects. As I just said, novel objects always appear in our household scenarios. So the second direction will be efficient scene representation. As you just see, even we can we are free of error and trials in target object finding, because our large language models can directly output, can predict what we need to find. But we still have the speed is still slow, as you see in the demo I just showed. We take 2 minutes to implement the stepwise plans. So how can we just accelerate this process? The first solution might be task awareness dynamic attention allocation, which is somehow similar to the multi-scale scene representation, because different tasks may focus on a different part of the scene representation. And the second one is a hierarchical sparse visual encoder, and we also have a paper accepted by ECCV 2024, and which means that especially for the house level visual clones, the house level point cloud, only very small part of the point cloud is useful for this instruction. For example, if we want to make a breakfast, only the potatoes. So you might imagine the scale of the potatoes and the entire house. So we can prune a lot of unused point cloud, and we just preserve the useful one for efficiency enhancement. Okay, let me make a brief summary. So our research just focused on the embodied visual perception in unknown environment. This is actually very important because we are encountering the dynamic things we don't know due to the human activities. And we have some challenges. The LLMs, because they have no awareness of the scene, so they may generate some plans with hallucinations. For example, they may generate to find a glass, but to receive the water, but we just have a bottle. So we need to let them to know this thing. And the second one is that the pre-built scene maps are not feasible due to the frequent changes in object locations and the existence caused by human activities. And the third one is that conventional perception models like conventional 3D object detection or instance segmentation models are very time-consuming in our embodied tasks like navigation, like embodied VQA, something like that. So we may need a real-time online 3D perception and a dynamic map update. So we propose two solutions. The first one is that we introduce an online scene representation framework that can build a representation. This can be used at any step. I mean, at any time, if you want to do object detection or instance segmentation based on current observation, it's okay. So at any time. And the second one is that develop the navigation algorithms to explore unknown regions on based on some common sense from grounded LLMs. So grounded is very important because if we just directly use GPT-4 or something like that, it has no awareness of the scene, so it may generate some hallucinations. Okay, thank you.
Thanks, Professor Wang. And anyone have some questions?
Okay, many thanks, Ziwei, for the great talk. I have a question. Have you tried to deploy this kind of model into the real robots?
Yes. Actually, you might see this part. Let me go back. So, I mean, this whole pipeline is actually, we need a planning, we need a navigation, and we need a manipulation. So currently, we have deployed our models on a mobile robot to find the given robot. But today, I don't show it on our slide. And after that, our next step would be, how can we actually do the mobile manipulation? This is actually very, I think, popular topic and also very challenging topic in robotics because mobile manipulation is very different from fixed-based manipulation. Because in fixed-based manipulation, the view of the camera is fixed, and if we want to manipulate something, we can collect a lot of the data like OpenX embodiment, and we can generate generalizable policies. But if we want to do the mobile manipulation, the first thing is that the views always change, the first thing. And the second thing is that, let's say we have a knife here, it points at this direction and the hilt is in this direction. Although we have a table here, we can navigate to every point, then we can pick up the knife. But if we just, the robot just stand in this position, it will grasp the point of the knife, so it's very dangerous. So we need to navigate to this location to grasp the knife. So this is actually a bi-level or joint optimization of the mobile base and the robot arm. So I think the policy space is much more large than the fixed-based manipulation. So it's very challenging. So we are currently working on that.
Yeah, thank you. And I've another questions. So I've also have a talk with a leader in the company regarding to this kind of home assistant robot, and he said the most important issue maybe now is for some corner cases or some long tail problem. Do you have any thought about this?
Yes. As Sherry just mentioned, building a word model or a digital twin is, I think, is a good solution for that one. And I think there might be some challenges if we want to build a digital twin or word model for like mobile manipulation, for example. Let me take that for example. The first thing is that the scene to real gap, of course. This is a common challenge here. And the second thing is that the cost for data collection of like mobile manipulation is very high. And to train the world model, we also need to collect some real world data. But how can we train the world model, or how can we build a digital twin with very limited human demonstrations? And I think this can be exploited with some advanced RLHF method for that.
Okay, thanks.
Thank you.
Any questions? Okay, yeah, please.
Thanks for the nice talk. Yeah, I have a question in terms of the, I guess in general, because I'm doing the simulation, and do you think I haven't seen that the simulation be applied to those real robotics? I guess they are still a very large room. Can you comment this maybe? What do you think for the future if we want to leverage more real world simulation to those robotics? How can we do that, and whether it's necessary or yeah, whatever, you have any ideas about this path?
Okay, very good question. And currently, we just face the challenges of large scale simulator with real physics. For example, if we want to do a mobile manipulation, currently we have we have some simulators like the OVMM, like the RoboCasa, and but they have their limitations. For OVMM, we can only do pick and place here, and for RoboCasa, it just have one room. So we cannot do something like a large scale room, but we may develop our simulators based on ISAC sim. So I think this is very important because you may see there are a lot of works on the mobile manipulation recently, and I think many of us just face this challenge. So I think it's very helpful if you can develop a simulator on that.
Cool. Sounds great. Thank you so much.
Thank you.
Okay, if you have no questions, this is the last section of our tutorial, and thank you all for spending the time and joining our tutorial today. Thanks.